This talk is Smashing the Font Scaler Engine in Windows Kernel. I'd like to give one reminder before we start to evaluate the session at the back of the room with your badge. It's really important to the organizers to know what you think. So thank you for coming, and without any further ado, here are your speakers.
Hi everyone, good evening. My name is Ling Chuan Lee, and this is my colleague Lee Yee Chan. And today we are going to talk about smashing the font scaler engine in Windows kernel.
Hello everyone. Basically, these are the agenda for today's presentation. First of all, we will go through the introduction regards the TrueType font. Then we will talk about the design of our fuzzer targeting of the TrueType font on Windows platforms. After that, the possibility of attack vector of the TrueType font, both locally and remotely, will be discussed and demonstrated. Lastly, we will demonstrate our finding of the TrueType font vulnerability that have discovered by our fuzzer. So basically, Windows support two broad categories of font, that is GTI font and device font. The GTI font, which are based in Windows, come in three types: raster, vector, TrueType, or OpenType. Here we would like to introduce the foundation of TrueType font. For instance, the outlines of a glyph outline consists of a series of contours. The font unit or F unit describes the TrueType fonts found, points location in the M square. The outline of the characters or glyph in TrueType fonts are made of straight line segments and quadratic bezier curves. In creating the glyph outlines, a type designer used an imagination square, which is called M square, typically as shown in the picture in the slide. The M square encloses the capital of Q. The grid is two-dimensional coordinate system, like x-axis describes the movement in horizontal direction, and y-axis describes movement in vertical directions. Okay. Actually, basically, this slide summarizes the process glyph to be displayed on raster device. First, the outline stored in font file is scaled to the requested size, and the scaler converts font unit to pixel coordinates and outlines to the size requested by application. The interpreter will execute the instructions associated with glyph and grid fits. The outline is then scanned and converted to produce bitmap that can be rendered on the targeted device. The scaler will create the necessary bitmap at a particular resolution. To solve the low resolution issues, each glyph includes a set of instructions that instruct the font scaler to modify the shape of the glyph. Okay. Font scaler consists of a set of API functions. During the reverse engineering, and we have identified few important functions for engine exported interface that include Win32 KFS open fonts, where this API function normally is used to initiate the font scaler process. Others APIs such as Win32 KFS new glyph, Win32 KFS control scan, and etc. And the API function also include for engine internal interface, engine converter functions, and engine support interface. And all these API are shown in this slide. Here are more API functions for bitmap related, instruction virtual machine, and for font structure parser. And in this section, we will discuss the bug hunting with our TrueType font fuzzer. In our TrueType font fuzzer, we will feed the Windows operating system with the crafted font generated by our fuzzer. There are two actions included in our fuzzer for every test case. Firstly, open the font file using fontview.exe, and secondly, display the default character map contents in the fonts file. Basically, fuzzing is divided into two categories, dumb fuzzing and smart fuzzing. The concept of dumb fuzzing is simple. It fuzzes the targeted file without concern of the file structure. It means that the fuzzer will do the byte flipping from the beginning until the end of the targeted file. Whereas smart fuzzing is totally different. It fuzzes with the consideration of the file structure, such as the relations from one section to another section. In the process of bug hunting, the file structure parser is very important to understand the hierarchical structure format. In this case, we develop our own TrueType font parser and OpenType font parser in 010 binary editor template. There are few advantages of 010 binary editor. First is it provides 30 days trial version and supports multiple platforms. Besides that, there are many free binary templates provided, such as bitmap, WinZip, media player parser, and etc. And this is the screenshot of our binary template using the 010 binary editor. Before we develop our own TrueType font binary template, there are many things we need to understand, especially the structures of TrueType fonts. First of all, the TrueType font begins at byte 0 with the font offset table. And this table is divided into 5 subtables that are SFNT version, number of version, search range, entry selector, range shift. And as mentioned previously, a basic font is composed of multiple tables specific in each header. A table name can have up to 4 letters, and this slide shows the header of a TTF binary file. The fonts table directory entries is followed after the font offset table. Each font table directory header consists of 4, that are tag, checksum, offset, and finally length. And here is the example of fonts table directory. As you can see, each value of the fonts table directory has relatively with the particular font's payload. This slide lists the required tables in font offset table that include CMAP, glyph, head, HSEL, LOCA, MASP, and etc. However, they also can include some optional font table, such as CBT, EBDT, EBLC, EBSC, and etc. And some more. And all the tag name for each table must register under Apple Developer Technical Support. For the TrueType font fuzzer, please remember that never ever use dumb fuzzing methodology to do the byte flipping for these 4 fields, that are checksum, offset, length, and table. Checksum calculation is very important in order to verify the verification of a font table. If the checksum value is wrong, it means the font file will corrupt and the fuzzing process will fail. And the Python code in this slide represents the calculation of checksum value for the data section while doing byte flipping fuzzing process. Another thing we need to highlight is that the checksum calculation implies 4 byte boundaries for the entire tables. It means that if any remaining space, it will paid with zeros. Besides the checksum values, another important values are offsets and length values. The offset values should always point to the beginning of the data structures, whereas the length value must always equal to the size of the data. Therefore, during the fuzzing process, the changing of every data location and contents should always update the particular values of offset and length under the font table directory. this slide shows you how the smart fuzzing technique can be used to fix the checksum value. As shown in the slide, the byte flipping changed the first byte of contents from 00 to 01, and our code will update the new checksum value for each byte flipping test case. So now let's jump to the TTF font fuzzer. Fonts can be fuzzed via different methods, either 1 byte, 2 byte, or 4 byte flipping, and etc. However, no matter how the targeted font is fuzzed, as mentioned earlier, the value of checksum, where every byte flipping test case is required to fix the checksum value. Some important functions are needed to ensure the fuzzer works. The first is log font structure. This structure plays an important role in terms of defining the font attributes. Calling the create fonts indirect function should able to return a font handle. However, the function is unable to work with lower level fonts API. Therefore, the API functions such as get font data, get glyph index, or ext text out with eto glyph index flag able to fix this problem. To summing up the overall process of the fuzzer, there are 3 important steps. First is the font fuzzer will automate the installation of the crafted font in C Windows Fonts folder. Secondly, the fuzzer registers a window class and creating a new Windows to display the font text. Lastly, it will uninstall the font from the C Windows fonts folders. And this slide shows the partial program of creating a log font object. The log font structure is called to define the attributes of a font, such as height, width, and etc. The add font resource ex function adds the font resource from the specified file to the system. The create windows function creates a pop-up or child window with an extended window style. And as soon as the attribute of font is well defined, the character map of a TrueType font has to be defined as well. Without defining the character map, even if a particular font encounters problem, the vulnerability will not be triggered. Defining a character map is very subjective, where defining the entire fonts of particular fonts will be a good option. However, the performance of the fuzzing process also will be decreased since it is designed to call the entire character map. Therefore, in our fuzzing program, we define to display the popular font that is from character 0 until character 255. We also define the font size range increase from size 1 to 100. And the size, of course, may change anytime if you want, but please remember that the font face name must change according to the name of the font you would like to test. Some Win32 API functions provided by Microsoft to call the physical font could be used by applications that need to work with fonts at lower level. In this TTF fuzzing design, we use ext text out w API function work together with eto glyph index flag. This slide shows the screenshots of our fuzzing process, and as you can see, the fuzzing is displaying the crafted font via fontview.exe, but the text displaying process failed because of the invalid TrueType font. So I'll pass the rest of the presentation to my colleague.
So I will continue the section. In this section, we will go through the fuzzing infra we have been set up for our TTF font fuzzing purpose. And auto fuzzing in cloud service is common today, but for us, there are 2 things we are very concerned. The first is the cost of cloud service is expensive, and the hardware spec for us is not so at once. And the second thing is we will disclose our sample and POC to the vendor. And finally, we decide to use 2 custom built server with memory 32 GB, storage 1 TB in our fast farm specific for TrueType font fuzzing on Windows platform. Each of the server running Ubuntu operating system and able to switch on 16 to 18 Windows 8 Pro operating system. And total fast case per day is around 300,000. And we use the advantage of Windows 8 OS, where the kernel debugging able to be connected through network, and this make the reverse engineering easier than previous operating system. And the setup process is very simple. You just need to run execute 2 commands in debugger operating system to configure the port number and debugger IP address. And the result of the command will generate the key. And in the debugger OS, you just need to launch and execute the WinDBG with the key and port number you configured previously. And the overall of our fuzzing infra is shown in the slide. And this is the physical, how's the server look like. And now I would like to talk about something regarding how to launch the Windows kernel font attack vector. And the GDI actually has long been identified as a significant kernel attack, and it is part of the core operating system component. And based on our research, we have identified that the GDI is one of the most easy accessible remotely. And as mentioned previously, the GDI font based in Windows consists of 3 types that are raster, stroke, and TrueType. But the rest of the presentation slide, we will only focus on TTF. And with the probability of the usage of the font, the vulnerability of font has been identified as one of the likely weak points and accessible via various computer applications such as browser, Microsoft Office document, Adobe Portable document, and etc. As soon as a vulnerability font is identified, the attack can be launched from local and remote to increase the attacker privilege as super user. And of course, the local Windows kernel exploit always is the most straightforward by copying and executing crafted font on victim computer. And the remote attack is possible by using a little trick to embed the crafted font in Office Word file or through web page. And here's the example of crafted font that open in victim computer in order to raise the user privilege as super user. As mentioned previously, we include 2 tests in our fuzzing process. The first is open the crafted font via fontview.exe, and second is displaying the default character map that is contained in the font file. And in a web-based attack scenario, an attacker could host a malicious web page that is designed to exploit this vulnerability and then convince a user to view the web page. And of course, attacker cannot have no way to force user to view the attacker control content. Instead, attacker would have to convince user to take action. For instance, getting them to click a link in an email address or in instant message that take user to the attacker web page, or by opening an attachment sent through email. And as you can see, the attacker can easily use CSS font face property to easily embed the crafted font onto the web page. And beside the web page, the remote attack could be launched through a crafted Microsoft Office Word file. Amended font into a Microsoft document not as easy as amended into a web page. Before embed the TTF into Microsoft Office file, the TTF font format has to convert to ODTTF file format. ODTTF actually is an amended font file type used in Microsoft XPS and Microsoft Office 2007 format. And the file type refers to an obfuscated subsetted font based on the font used in the original document. And the file can be extracted from the docx by renaming the file to zip, and so the archive can be browsed and extracted. And to perform amended font obfuscation, a 128-bit or just 16-byte of GUID is generated for the font to be obfuscated. And as soon as the Microsoft document is renamed and unzipped, the Office file is adopted an XML-based file format. And this new file format able to improve file and data management, data recovery, and extend the support with the earlier versions. And to force the docx to use the crafted obfuscated TTF font file, fonttable.html file which is located in Word folder has to be edited and set the value of W font key to perform an XOR operation on the first 32 byte of the TTF font file. And this slide shows the program of perform the XOR operation for GUID key with the first 32 byte of the TTF binary file. As shown in the slide, the odd value of the first 16 byte of the TTF binary file will perform the XOR operation with the GUID key from key 15 to key 0, byte by byte. And to explain more detail, the first byte of TTF font equal to value 00 will perform XOR operation with the key 15, which is equal to 34. And this process will be continued until the end of the key 0 perform XOR with the 16 byte of the TTF, which is equal to 46. And the same operation will be performed for the next 16 byte of the TTF font file. And inside the document.xml, we can define the font name in the WR fonts and W ASCII element. We also need to define the font size at the WSG and WSGCS element. And font size in the document.xml is expressed as half point value where value 80 in this case equal to font size 40. And for this research, we also come out some simple script to simplify the process of embedded the TTF in docx document. And here in this section, we would like to share some findings of our fuzzing process. Microsoft provides a very cool WinDBG extension, so-called exploitable plugin to evaluate the crashdown file. The tools was created by MSEC security team, and now the latest version even support ARM. And by the way, our experience tells us that the tools does not help in Windows kernel crashdown analysis. We still need to depend on existing WinDBG command on analysis. For instance, analyze -v or tracing kung fu like such as PH or TH. You also may consider VirtualKD combined together with the VMware and VirtualBox to improve your kernel debugging performance. And before I start to talk about some bugs in TTF, I would like to explain a little bit more detail regarding what is a graph and FPGM. The FPGM is used to define function and instruction. There are two functions, ITRP_FDEF and ITRP_ENDF, used to define a block of code as routine with instruction. And after the definition, we could call and execute the function using ITRP_call or ITRP_loop call in graph instruction. The graph tables basically is the table must contain all data required to construct the complete character set as specified by CMAP table. And for the first finding, the mutation happened at flag 65 until flag 78 and x coordinate 0 until x coordinate 39. The mutated flag value and x coordinate value will be processing in function fhg_execute graph, and the controllable x coordinate value in function Edwards-Muscan will cause the copying process override to non page area kernel memory. And as you can see, WinDBG extension exploitable plugin does not help anything in reverse engineering. And we need to execute a command like analyze-v to get detailed information. As you can see from the slide, there are override of non-page area memory at the instruction Win32K Edwards must scan plus 5B. And here I would like to do some demonstration. So basically our fuzzing infra is, this is VMware running Windows 8 Pro operating system, and this is a Windows 7, it's running WinDBG. So both systems actually connected through kernel debugging through network using WinDBG. So go to desktop. If you refer back to the folder, there is a source font fuzzer.python file. I use the py to exe to convert to the exe, and this Python file is used to call the crafted font fuzzer_2.ttf, which is able to crash the Windows 8 Pro operating system. And all the crash process were monitoring by WinDBG. So as you can see, the crash process will intercept by the WinDBG. And this slide shows you the second finding of our fuzzing process. The picture at the top is FPGM table in crafted font. ITRP_execute process the instruction of FPGM table and define a routine of broke code started at offset address 13A3 until 14.2F. And this allows us to control the range value in the fnt_function define structure and override the number of bytes to execute larger than normal. And this will cause the infinity loop call for ITRP_call execute in grid table will cause the Windows kernel memory exhaustion. As you can see, the WinDBG extension exploitable does not help in crash dump analysis and just provide a very simple information. And against WinDBG command analyze-v provide more detailed information regarding the crash dump. And here again, I would like to do some demonstration. For the bug 2, for the second bug. Then basically in this folder, as you can see, there is a crash.html. And this crash.html is configured the font fetch, which is a font name we are going to call, is equal to droid. And this is calling the fuzz_2.ttf, which is inside the same folder, and the format is equal to TrueType. And currently, we are calling the font size equal to 9. And the character map we are going to call is 312. So you just open and display in Google. You need to put a full screen. I believe this is a resolution problem in Google Chrome cannot display. Never mind, we move on. So I try to show the second remote kernel, and this is a library folder. In this folder actually contain all the important components to generate the docx file. And in this folder, Word folder, as you can see, document.xml, in this XML file, we configure is calling the droid font face and font size equal to 9. As I mentioned before, you have to divide it by 2, and the character map, character index we are going to call is 312. And this is a crafted font, and this is a Python code which we are used to generate the docx file. So if you refer to this source code, you're calling the fuzz_2.ttf and pack it to become the sample.zip and convert to the sample.docx file. So we go to command prompt to execute the Python code. Python TDF. As you can see, the TTF amended docx.python file is convert the TTF file to ODTTF and insert into the library folder and generate the sample.docx file. If you open the sample.docx file, you will cause the Windows 8 Pro operating system denial of service. And this is a third bug and fourth bug. Also is a result of mutation FPGM tables. And currently, actually, we focus on certain font sections such as glyph and FPGM table only. For instance, bug 1 is belong to mutation of glyph table, and bug 2 and 3, 4 is the result of mutation FPGM table. Many crash dump cause the denial of service in Windows kernel, but for the exploitation, you need to use some trick or creativity to execute the shell code after you control the EIP or able to override the parameter of fnt_global graphic state type structure. And some bugs are very interesting and able to embed into Office Word file and HTML, and some are not. And here is some note we would like to share. First is focus on a few glyphs before you start to fuzz, or else the root cause finding process is going to kill you. And you could include 2 tests for the TTF font file. For instance, open the TTF font file using fontview.exe, and second is calling the index from character set that is display the text in different size. But remember, never ever fuzz the TTF font file start at font size equal to 0, and it's because many applications such as Microsoft Office Word file does not support font size 0. And there are many open source tools help you on TrueType font fuzzing and editing. For instance, FontFox, FontTools, 010 binary editor, and Virtual KD would help you in set up your TTF font fuzzing infra. They also have many excellent and expensive tools able to help you on font editing such as FontLab Studio, Fontographer, and Bitfonter. And that's all for our presentation today. Thanks. Any question? Yes? Sorry, come again? You mean it's customized or? It's totally developed by us to pass the TTF font file. And in the internet actually, got one TTF font parser is shared by the guys from Europe. You can refer it, but it's not complete. Because some section, because TTF section is very complicated, like EBSC, EBLC, and EBDT. You can refer back to that code to further and add in more section you want to pass. No, this parser actually is a fully code by us using 010. And we are going to share all the things in internet after this talk. Pardon? Yeah, this is such a good question. For the bugs one actually is exploitable, but currently we're still working on the shell code because our shell code actually got a minor problem to execute in Windows 8, and this bug actually is reported, and the patch already released last 3 weeks ago. It's a CVE 2013-3129, if not mistaken. And the bug, and the second bug and third bug, and the second bug actually is just a denial of service, because after we analyze the second bugs, it just caused the infinity loop call in Windows kernel. For us, it's not exploitable. It's just for fun, yeah. But it's able to embed it into the OCX file and send to the end user to launch the remote kernel denial service. And we already submit to the Microsoft for this second bug. And regarding the third and fourth bug, actually, to be frankly to say, I have no time to representing the third bug and fourth bug before I come to this conference. But the bug 3 and bug 4 actually is also an FPGA mutation. Pardon? As my experience in last year, I tested in Windows 7 before Windows 8 release. Actually, the GDI attack, you don't need to care about any restriction. It's just direct hit to the Win32k.sys file, and you can use some trick to totally fully control the. Come again? You mean this exploit? As I just now I already mentioned, the first bug actually we have some issue in shell code. Hopefully there's everything is to be fine. Then we'll release in internet next month. The first bug, and the second bug actually for us is just for fun. Yeah, for us based on our analysis, it's just for fun denial service, but it's a little bit dangerous because you're still able to insert into DOCX file or HTML file, to launch the remote denial service to the end user. And the bug 3 and bug 4, we have no time to reverse engineering yet. Yeah, thanks. Any question? To be honest, actually we have 6. And one is two of it already reported. The other 4 we still pending, and we need some time to reverse engineering and confirm. Because some bug actually is just a bug. It's like software defect. It just caused the denial service. It's no meaning at all. But for TTF, the case is very special because you're able to insert into HTML, insert into DOCX, and have some fun with your friend, send to them, ask them to open it and crash their system. But it's not exploitable. Yeah. The first bug, yes. How many days of fuzzing?
How many iterations?
Iteration.
How many different
Different.
did you try?
Basically, you just try one. We just try one. Based on your question, you not need to. Based on if you're doing fuzzing, it's not good. You just randomly pick the font file, and
Running 300,000 a day.
yeah.
How many days did you run before you actually found?
I started in last year August. So 6 months after 6 months, I got 6. The other 2 maybe it's a false alarm. I don't know. We got 6 actually. Yeah. And the TTF actually is very complicated in process. Like if you want to reverse engineering, the process is very huge. From the starting how application to starting to call the TTF file and display the text is very complicated. And second thing is, if you want to insert into DOCX file, HTML, some font, you just double click and will cause your system denial service. And some after you insert into DOCX, you just no response at all. So you need to keep testing and testing and testing again. And my advice is, if you want to do fuzzing in TTF, you don't need to go for many TTF font sample. You just concentrate in one, because one enough for you to do the fuzzing, because the structure is very complicated. You just concentrate in certain glyph. Other glyph, you just use the tools to delete it. Because the root cause, if you get locked, you find a box. The reverse engineering, if you just want to, your font file is contain all the font set, all the character map, the process is going to kill you. So you just delete all the glyph, just concentrate in 2 and start to fuzz it. So if you get locked, you get the crash file, you start to analysis, the process will become more easier than you just simply grab the TTF file and fuzz it. So before you get started, you have to design, you have to think first the way how long you can go. I mean, you need to simplify your process first before you go to fuzz something. Any question? Yes?
What led you to fonts as an area that we get into the fuzz? Did you have some intuition initially, or
What line?
what made you think that, the font parser is something I should fuzz?
Actually, the TTF fuzzing is if you refer back to CVSS, there are many TTF font bugs is already reported, and just only one is rest is catch all the attention in the world is Dougal worm. Because Dougal worm is success to embedded into the DOCX file, and there are 0 days to launch the attack in SCADA system. And what made me to start to fast the TTF is because of, the first is for the IE, many people is doing IE fuzzing, browser fuzzing, Google Chrome, and for the DOCX, I believe Tom from Microsoft, Ben Nagy, they are doing this, and TTF, as I know, just my friend in Russia, his name is, I can't remember the name, and he and me only is doing a TTF. So I believe we still get a very bright future to get the crash. Because my thinking, if you want to start to fast, many people start to fast a browser. Why not you start other things out like Bluetooth, fuzzing, then you can get high chance to get your crash file. But to be remembered is crash file doesn't mean that it's exploitable. It still depends on how creative you are to analyze it and insert the cell code and exploit it. So the process is totally different: fuzzing, analysis, and exploitation. Any question? If no, thank you.
Device. The scaler will create the necessary bitmap at a particular resolution. To solve the low resolution issues, each glyph includes a set of instructions that instruct the font scaler to modify the shape of the glyph. Okay. Font scaler consists of a set of API functions. During the reverse engineering, and we have identified few important functions for engine exported interface that include Win32 KFS open fonts, where this API function normally is used to initiate the font scaler process. Others APIs such as Win32 KFS new glyph, Win32 KFS control scan, and etc. And the API function also include for engine internal interface, engine converter functions, and engine support interface. And all these API are shown in this slide. Straight line segments and quadratic Bezier curves. In creating the glyph outlines, a type designer uses an imagination square, which is called M square, typically as shown in the picture in the slide. The M square encloses the capital of Q. The grid is two-dimensional coordinate system, like x-axis describes the movement in horizontal direction, and y-axis describes movement in vertical directions. Okay, actually, basically, this slide summarizes the process glyph to be displayed on raster device. First, the outline stored in font file is scaled to the requested size, and the scaler converts font unit to pixel coordinates and outlines to the size requested by application. The interpreter will execute the instructions associated with glyph and grid fits. The outline is then scanned and converted to produce bitmap that can be rendered on the target.
This talk is Smashing the Font Scaler Engine in Windows Kernel. I'd like to give one reminder before we start to evaluate the session at the back of the room with your badge. It's really important to the organizers to know what you think. So thank you for coming, and without any further ado, here are your speakers.
Hi everyone, good evening. My name is Ling Chuan Lee, and this is my colleague Lee Yee Chan. And today we are going to talk about smashing the font scaler engine in Windows kernel.
Hello everyone. Basically, these are the agenda for today's presentation. First of all, we will go through the introduction regards the TrueType font. Then we will talk about the design of our fuzzer targeting of the TrueType font on Windows. Here are more API functions for bitmap related, instruction virtual machine, and for font structure parser. And in this section, we will discuss the bug hunting with our TrueType font parser. In our TrueType font parser, we will feed the Windows operating system with the crafted font generated by our parser. There are two actions included in our parser for every test case. Firstly, open the font file using fontview.exe, and secondly, display the default character map contents in the fonts file. Basically, fuzzing is divided into two categories, dumb fuzzing and smart fuzzing. The concept of dumb fuzzing is simple. It fuzzes the targeted file without concern of the file structure. It means that the fuzzer will do the byte flipping from the beginning of those platforms. After that, the possibility of attack vector of the TrueType fonts, both locally and remotely, will be discussed and demonstrated. Lastly, we will demonstrate our finding of the TrueType font vulnerability that have discovered by our fuzzer. So basically, Windows support two broad categories of font, that is GTI font and device font. The GTI font, which are based in Windows, come in three types: raster, vector, TrueType, or OpenType. Here we would like to introduce the foundation of TrueType fonts. For instance, the outlines of a glyph outline consists of a series of controls. The font unit or F unit describes the TrueType fonts file points location in the M square. The outline of the characters or glyph in TrueType fonts are made of